So this is part 3 of the course. It's described as energy and energy transfer, and it relates to chapter 2 in the book by Sengal and Bowles. So what we're doing here is we're going to introduce the concept of energy and work and heat as methods of energy transfer, and then the first law of thermodynamics, which essentially ties energy, work, and heat together. So we look at the definition for thermodynamics. It's defined as a branch of science concerned with the transformation of energy into useful heat and work for engineering purposes. So the example there would be the rocket. We use hydrogen-based fuel being transferred to the thermodynamic system. So work and heat can be produced and ultimately pushing that rocket up into the sky. So we can see very clearly that the terms energy, work, and heat are very important for thermodynamics. And what this section is about is clearly defining what energy, work, and heat mean. So we'll start with energy. If you look up the term energy, if you do a search, Google search, it'll define it as the capacity to do work, which is a good definition. But from the book that we deal with, it's defined as a property that must be transferred to a system or a body to perform work on it or to heat it up. So the example there would be the hydrogen-based fuel being transferred to the rocket, which is the system. And you can see the heat being generated, and ultimately the work is the rocket moving up into the sky. The interesting aspect about energy, it can't be created nor destroyed, just transformed from one form to another. That's essentially the first law of thermodynamics and the conservation of energy. Thankfully, energy can be stored, and there are different ways down here that we can store energy, but it is a challenge to find other ways, more efficient ways of storing it, especially when it comes to renewable energies. The SI unit for energy is the joule. It's named after James Prescott Joule, who identified the mechanical equivalent of heat. So he demonstrated that a certain amount of mechanical work could produce a certain amount of heat, which ultimately led to the conservation of energy. So the SI unit is the joule, and its base unit is 1 kilogram meter squared per second squared. There's many different types of energies. If we start with a few examples, nuclear fusion, it's the way nuclear energy is produced in the sun under high temperatures and pressures. So what happens is the energy in the atoms is released according to Einstein's famous equation, E equals mc squared, where E is the energy, M is the mass of the particles that we're dealing with, and C is the speed of light squared. When that energy radiates out towards the universe, it can be converted into chemical energy in the food that we eat, for example. When we eat that food, we can turn it into kinetic energy by virtue of the movements of our body. It's also converted into chemical energy in the fossil fuels and biomass. When we burn them, we can release thermal energy. When we put the fossil fuels in our cars, we turn it into mechanical energy by virtue of the movement of the car. We can burn them and turn them ultimately into electricity, electrical energy to power our modern world. And we can also produce nuclear energy through nuclear fission here on Earth, which is the separating of atoms to produce energy as well. And looking at a few statistics, the 3 main modes of energy use globally. So the 3 ways in which we use energy, or the purposes we use them for, is for electricity, for transport, and for heating. And the sources of energy that we use to provide for these 3 modes, in the main, according to this chart from our world in data, comes from coal, oil, and gas. And then you can see there's a small amount from renewable energies and nuclear reaction. And the challenge, I suppose, for the future is to depend less upon these and more on the renewable energies. Looking closer to home, those three modes of energy use in Ireland, 41% of it is for transport, around 36% of it is for heating homes and businesses, and 22% is for generating electricity. If we look at the electricity component and break it down, we can see that in the main we use natural gas to produce our electricity, but the renewables are catching up. And then finally, if we look at that renewable share, we can see that in the main it's produced by wind. That a large portion of our renewable energy is produced by wind power. And then we have hydro and biomass. And I suppose solar will be one for the future, perhaps. Energy in thermodynamic systems can be categorized into two types. One type is called macroscopic energy. So we'll look at macroscopic energy now. Macroscopic energy refers to the energy of a system that can be observed and measured directly without considering the microscopic structure of the system. It's the energy that a whole system possesses with respect to a fixed external reference. And it includes kinetic energy, the energy associated with the motion of a system as a whole. It's the energy possessed by a mass m due to its velocity v, for example, the kinetic energy of a moving car. And potential energy is the energy possessed by a mass m due to its position in the gravitational field g, and measured from a reference data point z, such as gravitational potential energy or elastic potential energy in a spring. The macroscopic energy changes with velocity and elevation. So let's just examine that a little bit more. Here we have a weight raised up into the air, and it has all this potential energy, this capacity to do work for us. And we measure that by multiplying the mass of the load by the acceleration due to gravity by z, which is its elevation, in this case, from the stump. And when we cut that cord and it starts to decelerate down, the potential energy turns into kinetic energy by virtue of its movement. And we calculate that by multiplying 1/2 times the mass by its velocity squared. Another example would be the bow and arrow. You pull back the bow and arrow, you've got all this elastic potential energy in the bow. And when you release it, it turns that elastic potential energy into kinetic energy by virtue of the movement of the arrow through the sky. The roller coaster, you've got all this potential energy when the car is at the top with zero kinetic energy because it's not moving at the moment. Halfway down, half of that potential energy is turned into kinetic energy by virtue of its movement, but we still have a potential energy aspect due to the elevation. And then at the end, all of the potential energy has turned into kinetic energy in the car in its movement. Microscopic energy is defined, those top forms of energy are those related to the molecular structure of a system and are independent of an outside reference. It's the energy at the scale of individual atoms and molecules within the system. It includes the translational energy, the energy associated with the motion of molecules moving in space, rotational energy, the energy due to rotation of molecules around their axis, and vibrational energy, the energy due to vibrations of atoms within the molecules. So the atoms are rotating, vibrating, and moving around, and that's a form of microscopic energy. Now, nuclear energy is the energy stored in the nuclei of atoms, which is typically not considered in classical thermodynamics unless nuclear reactions are involved. So unless we split those atoms apart or join them together, then we don't have to take into consideration the nuclear energy aspect. So the main form of microscopic energy that we deal with in a thermodynamic system is called internal energy, denoted by a capital U or a small u per unit mass. It's the total microscopic energy possessed by a substance due to the microscopic motion and interactions of its particles, which includes the sum of all the microscopic, kinetic, translational, rotational, and vibrational energies in the molecules. It says down here, internal energy is closely related to temperature. However, the nature of the relationship can vary depending on the type of system and whether it's in gas, liquid, and solid, and the conditions being considered. So generally related to temperature. So if you zoom in on a glass of water, you see that there's at room temperature, you'll see that the atoms and molecules have an energy in them, rotating, vibrating, and moving around. If you increase the temperature, you'll notice that that activity is increasing. And conversely, if you cool it down, you'll notice that that activity is slowing down. So closely related to temperature given the circumstances. In the book, this illustration is used to describe the difference between macroscopic and microscopic energy when it comes to producing work. So macroscopic energy is organized, all the water molecules flowing in the same direction and able to perform work in the turbine. Microscopic energy of molecules is disorganized, random, and not able to perform work. So we have all this potential energy in the water due to its height. And as that water is released down through the gate down here under the dam, it's being turned into kinetic energy by virtue of its movement. And it's the potential energy being turned into kinetic energy that is driving those two wheels. However, if we were to heat the water up and increase its internal energy, that would not have an effect on the rotation of those wheels. All of the work is being performed by the macroscopic energy in the system. So once again, potential energy is the energy possessed by a mass m due to its position in the gravitational field G, measured from a reference data point Z. And we measure it by multiplying the mass by the acceleration due to gravity by the elevation. And the units are joules. Though if we drop the mass, we get the energy per unit mass in joules per kilogram. And it's the same for kinetic energy, 1/2 times mass by velocity squared in joules. Drop the mass, and we get expressed per unit mass in joules per kilogram. And the total energy of a system is the sum of all the types of energy that it possesses. In other words, the sum of its macroscopic in the forms of kinetic and potential, and the sum of its microscopic in the form of internal energy. And we can express that per unit mass as shown down here. There's another form of energy, and that's it's called mechanical energy in engineering systems. And it can simply be defined as the sum of the macroscopic energy in the system. In other words, the sum of the potential and kinetic energies. A couple of examples would be hydropower. Water stored in a reservoir at a height has gravitational potential energy. When released, it flows through turbines, converting potential energy into mechanical energy, which is then transformed into electrical energy. So down here you see the Three Gorges Dam on the Yangtze River in China. It was the largest hydropower station in the world in 2012, and probably since been superseded by other massive dams. So the other example then is wind turbines. Wind turbines convert the kinetic energy of moving air into mechanical energy, which is then used to generate electricity. So what we have is we've got wind flowing, and there's generally no potential energy aspect in it because it's flowing horizontally. So it's the kinetic energy in the wind, which is a form of macroscopic energy that is being converted into mechanical energy in the turbine shaft, which ultimately gets turned into electricity in the generator. So this example here is used in the book to define mechanical energy. So let me just explain and put it into context. Mechanical energy can be defined as the form of energy that can be converted into mechanical work completely and directly by an ideal mechanical device, such as an ideal turbine. So we have all of this potential energy in the water due to its elevation. As we release it, it turns into kinetic energy going down the shaft, which rotates the turbine blades and turns it into mechanical energy. If we assume that that mechanical energy then is ultimately turned into electricity in the generator, but if we assume there's no losses, in other words, that turbine is running at 100% efficiency, then all of the mechanical energy here, all of the macroscopic energy here is being turned into mechanical energy in the turbine. The simple analogy that you'll see on the internet is you hold up a hammer. It's got all this potential energy. As you bring it down, it's being turned into kinetic energy by virtue of its movement. When you hit the nail with the hammer, it's gone into mechanical energy to drive that nail home. Simple example to calculate a mechanical energy of a car at 1,500 kilograms going at a speed of 50 kilometers an hour. First of all, we need to convert the 50 kilometers an hour to meters per second. And then we multiply that by the mass and divide by 2 to get the kinetic energy, which is the mechanical energy in that car. In engineering systems and environments, it's quite common to want to distribute fluid through pipe systems. And the type of energy in those fluid systems is is a form of mechanical energy. But before I can explain that further, I need to introduce a few fluid mechanic properties. So the first one is mass flow rate. It's the amount of mass flowing through a cross-section area per unit time, denoted by m dot in kilograms per second. So if you can imagine 10 kilograms of water flowing through a pipe and flowing past a particular point in the pipe every second, then it would have a mass flow rate of 10 kilograms per second. Volume flow rate is the volume of a fluid flowing through a cross-section area per unit time, denoted by capital V dot in meters cubed per second. So now we can imagine 10 meters cubed of water passing through a particular point in a pipeline every second. That would have a volumetric flow rate of 10 meters cubed per second. And you can see that they are related to each other by density. So if you're given the volumetric flow rate, you can multiply it by density to get m dot and vice versa. But density is the inverse of specific volume. So we can also use specific volume multiplied by m dot to get v dot. If we know the energy per unit mass, we can multiply it by m dot and we can convert joules per kilogram into kilowatts, which is a useful way of expressing energy, as we'll see when we go through a few examples. When we're dealing with fluid flowing through a pipe system, one end of the pipe could be higher than the other. So there's a potential energy aspect there that we need to consider when we're calculating the energy, but the fluid might be flowing at a particular velocity as well. So the kinetic energy aspect comes into it also. But if something is pushing, if there's a pressure pushing that fluid through the system also, that's what we call flow energy or flow work. It's defined here as flow work represents the work required to push a fluid in or out of a controlled volume. This energy is associated with the pressure and volume of the fluid. So let's say we have a pump, a centrifugal pump, and the impeller is moving around. It draws in fluid through its eye, sends the fluid out used by centrifugal force at a higher volumetric flow rate and pressure. Now let's look at a more theoretical example. Let's say we have a piston pushing an amount of fluid through a controlled volume. The work, as we'll see later on when we cover work, is force by displacement. The force pushing that piston by the displacement of the piston. Now, pressure equals force over area. You may have come across that mathematical expression before. So if we transpose it, we'll get force equal to pressure by area. When we calculate work by force by displacement, the force can be expressed in terms of pressure by area, and then the area by the displacement is the volume of fluid that we're dealing with here. So that's how we can express flow energy or flow work in terms of the pressure pushing that fluid multiplied by the volume that's being displaced. If we divide volume by mass, we get specific volume. And we can replace specific volume by 1 over density as well. So the total energy, mechanical energy in a fluid system encompasses the energy associated with the movement and pressure of a fluid. This energy can be broken down into 3 main components: kinetic energy, potential energy, and flow energy. So if we've got fluid flowing through a pipe, we have to take into consideration any elevation there, pushing the fluid through the pipe system, and that's the potential energy. We have to consider any velocity in the fluid, and that's the kinetic energy component. And we also have to consider pressure in the system that might be produced by a pump, for example, to calculate the energy that's pushing that fluid through the pipeline. So this is the total energy expressed mathematically. If we divide by M, we'll go from joules to joules per kilogram. But just note that if we divide B, the volume, by mass, we get specific volume, which is the inverse or the reciprocal of density. So that's how we can go from PV to P divided by density over here. If we're operating between 2 points and we want to know the change in mechanical energy between 2 points, for example, in a pipe system, we get the change in each of those terms between those 2 points. If we if we multiply that in joules per kilogram, multiply it by mass flow rate, which is m dot in kilograms per second, we will get kilowatts. So m dot is kilograms per second, and the energy per unit mass is joules per kilogram. The kilograms cancel, and you're left with joules per second, or watts, the rate of energy. So let's look at an example here. We have an upper lake and a lower lake, and we want to find out how much energy is available in this system to put a turbine in there and produce electricity. So what we do is we get the difference between each term in this equation. And if we look at the situation, we look at the pressure term first of all, we'd see that but the system is open to atmospheric pressure at both ends. So P1 is approximately equal to P4, which is atmospheric pressure. So that term cancels. We'll see that we're dealing with surface velocities on the upper and lower lake. So those terms effectively cancel as well. So the only mechanical energy component is due to the potential energy in the fluid due to this elevation. Some books denote this elevation as H, and then some denote them as Z. So just to know, that should be Z in there. And the reason why we put it in as Z is because we don't want to confuse H with specific enthalpy, which we'll be introducing later on in the course. So we'll assume that H is a Z. And okay, so if we get the potential energy, which is the acceleration by the mass by the elevation, but we drop the mass because we're dealing with the energy per unit mass, and then we multiply it by m dot, which is in kilograms per second, we will get the energy available in terms of kilowatts. And in this case, it works out at about 3 megawatts, 3.6 megawatts. So we do put a turbine in there, and we want to know how much mechanical energy we're getting out of the turbine. We apply our equation again, and what we'll notice that the potential energy due to the height difference from one side of the turbine to the other is negligible, that we don't have to take it into consideration. We're dealing with such a small elevation. The kinetic energy change across the turbine, it's also small and negligible, and we don't have to take it into consideration. But there will be a significant pressure difference across the turbine. So we know that pressure difference, which would be easy to calculate in the real world by putting pressure sensors in there. We get that and we can find out the mechanical energy that's being produced by that turbine. And so we get the pressure term and multiply it by m dot, and we'll get the value in kilowatts that will be produced by that turbine and hopefully turned into electricity in the generator. Another example, a river is flowing towards a lake at an average velocity of 3 meters per second and a rate of 500 meters cubed per second at a location of 90 meters above the lake's surface. Determine the total specific mechanical energy change of the river water per unit mass and the power generation potential of the entire river at that location. So identify the system boundaries. We're going to analyze it between points 1 and point 2. So what we know is at point 1, the velocity is 3 meters per second. The velocity at point 2 is the lake. So there's no velocity there. It's a surface velocity. The lake is still. The volumetric flow rate is 500 meters cubed per second. The elevation is 90 meters. If we're going between points 1 and point 2, that'll come out as a negative value. And we assume that we're dealing with atmospheric pressure in the river and the lake. And as I said, V2 is approximately 0. We put them into our equations and we get minus 887.9 joules per kilogram. So that's how much energy per unit mass we have. There's a negative values because we're going in this direction. So basically what that's telling us is that we have all this energy and we let it go to waste and we just let it run into the lake. So that's why there's a minus value there. So it's up to us to decide, is that enough energy to want to harness by putting a turbine in there? We're giving the volumetric flow rate of 500 meters cubed per second. We need to convert that into a mass flow rate. So we multiply by the density of water, which is approximately 1,000 kilograms per meter squared. And we get this value here, 5,000 kilograms per second. Power generation potential of the entire river at that location is our mass flow rate by the excuse me, the mass flow rate multiplied by the energy per unit mass, and there's 444 megawatts available to us if we put a turbine at the foot of that river. There's also mechanical energy potential in the air. So with a wind turbine, there's an example here. A site evaluated for a wind farm is observed to have a steady wind speed of 8.5 meters per second. Air is blowing across a wind turbine at a mass flow rate of 1,154 kilograms per second. Determine the wind speed per unit mass. So all of the energy is basically kinetic energy. We're dealing with atmospheric pressure, so the pressure term can cancel. We're dealing with air moving horizontally, so there's no potential energy aspect to it. So all of the mechanical energy is basically the kinetic energy of the fluid flowing horizontally. So a half mv squared, but we drop the mass because we're dealing with the energy per unit mass. So it's v squared divided by 2, and it turns out at 36.1 joules per kilogram. Now it tells us to calculate the wind energy for an air mass of 10 kilograms. So we'll just put the 10 in there and we get 361 joules. But now it's telling us to determine the wind energy for a mass flow rate of 1154 kilograms per second. So we take part A and we multiply it by the mass flow rate. And we get 41659.4 watts, or approximately 41.7 kilowatts. Another important term in engineering is efficiency, and it's strictly defined as the desired output over the required output. So let's say you have an electric motor, for example. You want to know how much mechanical work is being done by the motor and divide that by how much electrical work goes in to make that happen. You can also express it in terms of power, so it's the power out over the power in. So in this particular case, what we're going to do is we're going to look at the mechanical energy out by the electrical energy in. We'll get a ratio that's between 0 and 1. We multiply it by 100 to get it into a percentage. So we can also express it in terms of work. So the mechanical work out of the electrical work in. So the mechanical work is basically the weight of this in kilograms multiplied by 9.81 to get it into newtons by the distance that we're going to displace it. And that's the mechanical work that is being produced by that motor. Then we divide it by the electrical work going in there. Now, electrical power is the work done per unit time. So it's easy to obtain the power by putting a watt meter across the motor, for example. But if we multiply that by the time it takes to lift that load, we won't get the work done per unit time. We'll get the actual work done. So that's why it's power multiplied by time. So we're getting the mechanical work divided by the electrical work, and we will get the efficiency of this motor. So let's say we have the upper and lower lake situation again. The efficiency of a process is defined as the ratio of the desired output to the required input. Power is the work done per unit time, and it's denoted by W dot. So we want to get the efficiency of the turbine down here. We calculate the mechanical energy in the fluid, and we get the mechanical energy in the shaft of the turbine, divide one by the other, and we get the efficiency of the turbine. If we look at the generator, if we get the electricity value coming out and divide it by the mechanical work going in, we will get the efficiency of the generator. And if we multiply those two efficiencies together, we'll get the efficiency of the whole system. And what we see then when we multiply these two terms together is that the shaft work in the middle can cancel. So another way of calculating the efficiency of this whole system is by getting the mechanical energy available to us in the power station, the water, and divide that into the electrical energy that comes out of the generator. So in this example, the turbine has an efficiency of 0.75 and the generator has an efficiency of 0.97. According to this equation down here, we can simply multiply those two together and we'll get the efficiency of the whole system. If we go back to one of the questions that we done earlier on, and what we have is we've got an upper lake and a lower lake, and we wanted to see how much energy was available in this system, and we worked it out to be 3678.75 kilowatts. But the system itself, the whole system, has an efficiency of 85%. So we multiply 0.85 by this value over here, and we find out that of that 3678.75 kilowatts, we can actually get 3126.93 kilowatts out of it because of the efficiency. So wind turbines have an efficiency generally of 20 to 40%. So a lot of energy goes to waste. You can imagine that the wind is quite chaotic, so it's difficult to grab and harness all of that wind. Petrol car engines, 25 to 30%. So we lose a lot of energy there due to heat being dissipated in the engine, due to friction at the road surface, and due to air resistance as well. Diesel car engines are a bit more efficient, and these values are more than likely have changed in more recent times as cars have improved their efficiencies. And large power plants can be up to 60% efficient. And where they lose their energy, that's at the condensers, as that energy is being released to the atmosphere so that the waste steam from the turbine can condense down to liquid and the water can be pumped back up to the boiler again.